will allow us to carry out the proof.
Okay, yeah, so the goal of this talk is to prove the commutativity of this diagram. Luckily, I guess the good news is, in some sense, nothing new will happen in this talk. Everything you need to do that has already been explained. And so you can think of this talk as an extended exercise or a quiz in what happened so far. But anyway, so let's start with the different components. So first of all, we have the Langlands functor. So very briefly, there's this question. Which factors through this localization? And well, we have the coefficient function, so backing coefficient function. So if you have the statement, as Sam already explained, or said again, in the last hour, this action, which comes by naive subtracting, factors through this quotient. This is a localization. So this acts here, and we have this our favorite functor, our favorite measure of a d bound to 1 by g, which is the vacuum coefficient. And so just because this acts here, this automatically gives you a functor. Just of course. And then the Langlands functor is a renormalized version. So, well, roughly speaking, this was explained, yeah? Well, anyway, let me say just in words, remind you what happened. So, roughly speaking, well, you want to replace this by a different category, but it's a category which has this, which only differs homologically at finite infinity. And basically, you require that the true Langlands functor agrees with the force functor. Is well, if you take compact objects in here, they are bounded, and so you can apply this functor and thought of as landing in that larger category and index them that. And that's the data course in the oops. Worse. So that's yeah. So anyway, so I won't say much more about that. And so, well, what do we know? Well, we have that. So a back functor G. Well, this factors via this Whittaker category. And the point is, both the factors. So the point is that this functor is equivariant for the Satake action. In particular, it's equivariant for the action of this category, rep G check run. And so, well, rep G check run is kind of free or co-free over itself. And so how this implies that we have a commutative diagram. Which is G Langlands functor. Here on the coefficient functor. Here we have the geometric exponential. Here we have this spectral localization functor. So let me just say a little bit more about why this diagram commutes. The point is that all the functors I wrote down are compatible with the symptotic, which means that, well, these are equivalent. So in other words, this diagram commutes if and only if, well, I further go convex. So kind of expressing both of these as free modules over this acting category rep G check run. Will be co-free. So this is the anyway. So this is invariance. This is the thing that gives the vacuum Whittaker coefficient, which in terms of the affine Grassmannian corresponds to taking the Schritt fiber at the identity. So because this commutes and all of these functors are compatible with the action, this automatically means that this time. Yeah.
We'll quickly review the definition of with G sub rho.
With G sub rho. Let me know. It's a great question. And I mean here this is some kind of E modules G that are kind of mod. That are equivariant for the unipotent part against the character.
What was the question again?
What is width?
Well, so specifically with G sub rho, but is it a rho?
So it's a wrong version of this. Yeah. Sorry. So this is a kind of a pointwise thing, and well, you see again, if you look at this like very naively, if you look at this formula, well, Burr you can take as the valence and Drinfeld Grassmannian, and this L kind of only depends on, like, you can kind of vary the point naturally, and it only depends on kind of the point in the Ron space, and so this kind of makes sense in a very straightforward way over the Ron space. Yeah. Sense. And
What's the difference? The left vertical.
this one?
Yes.
This one?
The lower.
Yeah, so this is Schritt fiber identity. That's the thing that gives the back and Whittaker going. Oh, okay. So we have more or less, like, this commutative diagram is more or less what defines the Langlands sum. Okay, great. So now we also have so that's the bottom part of this diagram. That's the kind of the tautological part. So we want to show, we'll state it as a theorem, is that this localization functor.
If you write something like it,
Yeah, sure. Do you want me to rewrite this?
whatever you want, just kill it.
Okay. Well, yeah, it's the I'm just rewriting that over there. E. Let's see. It's a category of monodromy free operators. And then we'll have the functor and hello. Okay, so this canonically commutes. Okay, so what's the plan? Well, of course, the way we're going to do it is use commutativity of this diagram. So roughly, what you want to say is that you post-compose with these functors, and then and translate this into a purely local question, and do the local calculation, and see that it commutes. So that's yes.
So just formally, once again, on the right, you take invariance and then globally integrate around, right?
This
This the low right vertical arrow on the right.
This one.
This one.
Yes, invariance and yeah,
Then-
I think this is what we were calling invariance before, but yes, you take. Yeah, if you think of an object here as something living over the Ron space with an action, you take invariance and then you integrate over the Ron space. Yeah. Okay, great. But the only problem is that this so this was spec of what it's called. So the only problem is, well, you can't quite do that. This would work if both of these functors were fully faithful, everything would be great. And well, they're almost fully faithful, but not quite. So to address that, it turns out that this is not a problem in this case, for the reason that both of these functors land into the subcategories where this does become fully faithful. So let me remind you how this works. So I guess in Dennis's talk, he introduced the notion of temperedness. So
We think it would be okay if functors were both faithful.
oh, I'm saying that so you want so you have this big diagram over here. Okay, we'll to this one now. So you want to prove the commutativity of the top diagram. You know that the bottom one commutes. We already have that. And so if both of these functors were fully faithful, well, then it would be enough to establish commutativity of the outer diagram.
Yeah, that's a super important point, and we need the recurrent theme.
Yeah.
So again, like suppose the bottom, like the right bottom vertical arrow was fully faithful.
Yeah. So if it was fully faithful, I mean, what does it mean to give the data of commutativity?
The right bottom vertical arrow.
Indeed.
So like if it were fully faithful, to prove that the upper square commutes, it would be enough to show that the entire square commutes. That's the logic. So that's what we're doing.
Yeah, I mean, again, naively, what are you trying to do? You're trying to give a natural isomorphism between two functors from here to here, one going this way and one going this way, and to give an isomorphism between things, it's the same as data as to give an isomorphism between them after applying a fully faithful function.
Could you just quickly say once more why going to vect commutes? Like, yeah.
Here, that's the definition of F.
Oh, by definition. Okay.
Yeah, this is the, so because this is the vacuum coefficient by definition.
Yes.
And then the functor here, that factors through here, well, whose coarse version factors through here is defined as take this functor and use and use the action. This thing. So that commutes by definition of L.
Oh, can you say a little more about so in that diagram, the outer sphere community type well problem.
This commutes?
Yeah.
Oh, yeah, because all the functors in the top square are functors that are that are linear with respect to this. And the point is both this and this are co-free as modules. And they're co-free on kind of on this thing.
Oh, what is co-free?
I mean it's like free, I mean imagine free. So it's like a free module, right? If you want to know that like a map from a free module is the same as some other map from a free module, well, you identify the generators, and if you can say that the generators go to the same thing, then the maps agree. So this is kind of the dual thing. Co-free is the dual thing for that. By the way, when did I start? When did I
started 10:20.
Okay, so 11:20 is that?
Yeah.
Okay, no problem. Any other questions?
So the free versus co-free thing, everything is related to that or another.
Yeah. Correct. I don't know if that's a thing that well. As a pedagogical question, I don't want to right at this moment get into the question of what rigid means.
Sure. Well, you can assume that one.
All right. Any other questions? Okay, so temperedness. Well, so we have this derived socket. Well, what it says is that the spherical category for G, the spherical category. Remember, this is yeah, modules. It's the derived equivariant category of that Bressonian. So this is equivalent to info on something point commodity check. Yeah. Where the monoidal structure here is given by convolution. These are, well, at least as monoidal categories. More than that, but for now, monoidal categories. And this particular category, this has a monoidal localization too, where I replace intco by quasi. Yes.
And the point of order, there's some renormalization happens.
Indeed. I don't. Indeed. Do you want me to say nil or?
Well, I remove or renormalize.
Yeah, I know. Let me. I don't know. We've been imprecise about all sorts of things. Let me be imprecise about this.
We kept this.
Yeah. And so let me just denote this as this spherical G tempered. So this is the tempered version. So something is tempered. So if I have, kind of as a general. If I have some category with an action of the spherical category, well, then I can form the tempered version. I forget, is there an official notation for this? Superscript temp is a. Okay.
Subscript doesn't matter.
It's okay. So this is defined as this is defined. Well, you just take the full subcategory where the thing factors, where the action factors through this localization, which is the same as taking this TensorFlow. So an important point is that this is a full subcategory.
Let's see over there.
What's that?
Let's see over there. What's it?
Doesn't matter.
Yeah.
Okay, let's not waste time because we'll,
Yeah.
we'll. Limited.
Yeah. Yeah, indeed. Let me know what's
Faithful, but that's under, is that under a continuous functor or is that a writing form?
it's a continuous function. I mean, basically, the reason that this is the way you prove that this is fully faithful is that there's a continuous right adjoint there, which is a module functor, and so tensoring preserves the junctions and preserves the unit being an isomorphic.
Continuous left adjoint.
Continuous, sorry, left adjoint. Yes, thank you.
Like, let's say I didn't know the rest of it. Can I still define this considered variable category? Like purely on the.
No,
No,
you need to write stuff.
yeah.
No, the Dario is.
No, it's still the right.
One way or another, I think there is no definition that doesn't use direct Sataki. There's direct Sataki in that story.
But I think Fuji can be say is the right conclusion. Fuji.
That's true, but
Thanks, but this is a.
Anyway,
I know
let's,
we're gonna stop. Let's move on because then
let's-
we'll get where we need to get to.
yeah, let's postpone that discussion. Oh, okay, so what you'll want to say. So the yes, very good. So we define, so in particular, we can apply this to D modules on func G. We can consider this subcategory.
If it's important. Yeah. Yeah.
What's that?
If it's important.
Great question. Great question. Yeah, so you pick a point and you define, and you have that. So indeed, this action depends on a priori depends on a choice of point. So a theorem, I guess of Joachim and Sam, is that it actually doesn't depend. This category doesn't depend on the choice of point, even a point in the wrong space. So let me know. I don't know, Joachim will say something about that.
We don't need this theorem because we only need. That it's on the, we only.
Yeah,
on the spectral side where it's,
Indeed, and on the spectral side, it's obvious.
yeah, we don't need this.
And so what the first observation is that the Langlands functor takes this tempered category. Tempered. I guess I should have said. This Langlands functor. It was a priori constructed to be equivariant with respect to the naive Sopocki action, but it's actually equivariant with derived semantic. And just state it as a fact. L means
Is it something complicated?
what's that?
Is it something complicated?
No, it's not something complicated.
It follows formally from this lower diagram that's straight to the big. So once you believe that it commutes with this, because Casa-Manchalaica commutes with derived attacking, it follows formally that
Yeah.
functor commutes with derived attacking. Again, first we apply the conversion and then you upgrade it to the conversion.
Yeah,
But the
and
same procedure is in my job.
Yeah.
So that's the answer to this question.
Thank you. It commutes with three actions. That's one, and now the observation. Maybe let me say that also as a fact. Is that if we look at int conil. Now the tempered part. This is exactly quasi-coherent sheaves. I mean, part of the idea is that this notion was defined, was rigged for this to be true. So I mean, there's some analysis about how this action works, but it's kind of a very geometric statement. And so the upshot. So of course, the tempered category goes to the tempered category, so that the Langlands functor takes the tempered category to, well, quasi-coherent sheaves. Systems. I'll draw this as a commutative diagram. This includes all the modules. So there's a commutative diagram of this. Okay, great. Great. So far, I don't want to erase this diagram. We're about to get to it. And now the point is, so what's the saving grace of the fact that of the non-fully faithfulness of this is that both of these functors, the localization and the spectral Poincare functor, land in the tempered subcategory. So the reason for this, facts. So this was already mentioned in Dennis's talk, that the tempered part. So again, I should say that basically all functors in this diagram commute with the sphere with the action of sph. And so in particular, they'll take tempered things to tempered things. And the tempered part of the Cauchy-Lewis category, well, it's already tempered. So this is just KL. So this was, well, Dennis at least stated this fact. And similarly, on monodermally free uppers, star, we really should decide where the star goes. Tempered is itself so let me briefly explain why that is. So essentially, a proof of this fact was already stated in Dennis's talk, because this category.
Isn't this fall?
Yeah.
That was Kevin mentioned it. So like,
Oh, okay.
yeah. So it does follow from the affiliate, but
This is much simpler. It's not totally simpler. So it follows from the following thing, that there was the tensor product formula for this, where on the left-hand side was quasi-coherent sheaves, where one of the terms was quasi-coherent sheaves on local systems on G-check, and the SFO acted via that. And there was a subtle point of identifying two a priori different actions of the spherical hyperpath. But anyway, this was the thing that was explained in Dennisist. Yeah.
Nick, do you need to?
What?
Do you need two for the argument you're making? I think you only need one.
Yeah, you only need one actually, so it's okay.
Indeed, I only need one, but yes, but it's nice to
It's all good. Let's move on.
indeed. I mean, this is a useful fact. Anyway, let me. It's at least cleaner to stay. Anyway, but yes, I agree. You can get away with less. Okay, so what's the? What's the upshot? Is anyway, just directly to your question, is I wanted to avoid using the FLE equivalence as long as possible.
But you don't need the example.
Well, I mean, I agree.
Yeah, but you need to know that the bottom composite goes to tempered, right?
What's that?
I think you need both, right?
Well, you need to know that the bottom composite goes to tempered, but you know that from the fact that FLE is an equivalent.
Oh yeah, like if you know, like I mean, but then you use this as well.
Well, anyway.
Yeah.
Certainly what I said suffices. So the upshot means that we have the following diagram of this layout. This localizes to the tempered part. Well, I guess I should say that this L is more or less tautologically this L, the way that L was constructed on the whole category, that what we get is on the tempered category. This L is exactly the restriction of the force version to this tempered. Of course. It's very good. Tempered category. Use that. Oh, yes. Oh, Okay, so we have now we have this big diagram. What's that? Yes. Thank you. So the point is, so that the difference is I added this line, but now the point is this composite here is fully faithful. And so, well, to show that the commutativity of this square it's enough to, this one obviously commutes. By definition, so it's enough to show the commutativity of this one, which is enough to do it after post-composing on the ultimate target with a fully faithful font. And so what we arrive at is that we need to show the commutativity of the outer diagram. Does everybody follow that?
And the vertical fully faithfulness on this contact part is previously shown.
Oh, this composite is full faith.
Yeah.
Well, I don't know. It's been asserted. I think maybe it will be explained in a future talk.
What?
The fully faithfulness of
So what we asserted, like day one, is that the left adjoint of this, which we call log spec, that was a quotient.
yeah. I guess the question is whether that will be explained. I mean, I guess that could, if not, it could be explained in the Q&A session.
Yeah. So it's in fact, it will be a very late fact. Will be explained in the latest talk tomorrow. Very late fact, and so this.
Yeah. So there you go.
Postpone until tomorrow.
So.
Let's put it like
Certainly not explain it now for reasons of time. Not getting derailed, but so let's yeah. So we need to show. Commutativity of this outer diagram. E we need to show so we need to show commutativity of this diagram. And again, well, I guess we can do this maybe to simplify matters. Let's observe that everything is again equivariant with respect to the action of the spherical Hackett category. So it's enough to just go down to that. Oh. Yep. Yeah, so where this is again variance. Yeah. This over here, this is vacuum coefficient. So in fact, it's enough to show this outer square commuting. Again, because of compatibility of all of these functors with the, I guess, enough to know rep G check raw action.
So of course, it's critical actually the unit of the magnetic cell also belongs to
For which? So when I talk about the action of the SFO, that involves the on the whatever this category is on the spectral side, that involves derives. But here it's only this part of it, which is nice, but more is true.
So direct Sadaki appears in the definition of temper.
Yeah, so in this story, that's kind of the only place that derived Sadaki appeared. After that, if you believe in some basic things about temper, you can forget about derived Sadaki. This is only using naive Sadaki. All right.
If you also use the US with respect to the rest.
to get to here.
Yeah.
Yes. Well, I mean, to say the only place I've used derived Satake is in kind of properties of temper. Okay. But now we're in great shape. Precisely because Lynn told us what this composite is in local to global terms, and Kevin told us what this composite is in local to global terms. So let's compare them. What does Lynn say? That this composite followed by the vacuum coefficient. That given by, trying to get this right. Well, we had this enhanced version. Forgot if I'm supposed to write bars somewhere or not, but some enhanced version of the Drinfeld circle of functors, which goes to modules, factorization modules, over the factorization algebra where Z is the center of the vacuum module at the critical level. And then after that, we do chiral homology, factorization homology. Yeah. So that was that. So that's what this composite is given by in the local to global terms. And Kevin described what the other composite looked like. This here. Okay, by the use of notation called gamma spec, also the functor to the maybe just gamma, don't know. Yeah, that looks good. Because that is the functor of global sections. But this composite is given by this functor. So you take info lower star of monodromy free offers. You push it forward to info lower star of meromorphic offers. We carefully write this. This is monodromy free. This is meromorphic. Let's not confuse the two. And then this, remember, up to T structures is the same as this category. Oh, precisely because because of the Fagan-Frankel isomorphism, which identifies this with functions on regular offers, and then the rest is the same. Okay, right. So these are the functors we want to. These are the functors we want to compare. And so we have to remember something about. I mean, in order for this to make, in order for any comparison to make sense, we have to say something about Casimir-Shalaika and FLE. And so the key point, this was more or less explained in Dennis's talk, is
No definition like
oh, sorry.
Yes.
Yes. Yeah, sorry, indeed. We already took global sections. Yes, I agree. So well, we have one way or another, we have to say something about FLE. Well, the point is that FLE is constructed. So we have to slightly open the box of the construction of the FLE with the so that, and it's almost determined by this, that if you start with KL, you apply the FLE. And then you push forward to neuromorphic offers is the same as agrees with this other composite. Well, when you first, we're going to use the notation from Dennis's talk. When you first forget the integrality with respect to G of O, and just think of it inside of all of Kac-Moody, so this maps to with star of Kac-Moody. And then, lo and behold, there's the kind of the same. See, there was a Dernfeld-Sokolov functor there, but there's also a Dernfeld-Sokolov functor in the definition of the FLE. And this is what is responsible for this commutation. It's also some version of the hands going to int O star check neuromorphic. So this is exactly the statement. So this exactly implies that well, when you go to FLE, so statement, so you have FLE. This identifies with chat. Free. So over here, you have the push forward functor to neuromorphic offers. And on the other side, the way that the thing that makes this commute is well, you map it to Swit star of AM, and then do this enhanced version of Dernfeld-Sokolov, and so this commutes. And I just rewrote what this says. And well, the point is that in both cases, the functor, that on that board, this VS contains is exactly the composite of going here, of going this way, and then kind of more or less, and then going to this renormalized version of factorization modules over the center. And so the point is these are the same, like even before taking factorization homology. And so, well, and so they commute. This is the argument. Thanks.
We're done.
We're done. Yes.